Hi, Michelle. You're saying good afternoon or good morning for you. That's all. I'm quiet here, and we're working our payload. We have to deliver our payload at middle of May, and we're dead scared now.
Oh my. Oh yes, crunch time.
Yeah,
That's a great view of your lab.
I'm sorry. It's a whole mess.
It is
And,
awesome.
and you just talk about coffee. I needed to get a coffee.
Yes.
You remind me I need coffee.
Yes, cheers to you. This is for us. Yes, coffee.
Let me see if I don't make a big mess here.
Oh, but wow, look at that. It's beautiful.
And it has a neural network processor, NPU, with 26 data operations per second
Wow.
for doing AI during flight and doing the analysis of the data collected in
All
parallel
right.
as being collected and stored.
Fantastic.
So yeah, it's coming up. I keep quiet, that's all.
Welcome, everybody. It's the 21st of April, and this is Open Research Institute's FPGA Projects Meetup. And we talk about what we have done, what we have planned to do, if we have any roadblocks, anything in our way, and if we have any resources that we need that ORI can help provide or find or support you with. Well, so let's open with Aaron's work on OpenCPI.
Good morning. Let me share my screen. All right.
Yes.
So, like Michelle said, I'll go over the accomplishments and what's planned for next week and any roadblocks. So last week, I designed this guy, a little logo. My slides were kind of plain. So when I think high flyer, I think of a kite. So that's where I went with that. And then obviously we're doing a satellite, so I created that. Um, it's just a proposed logo. But just a status update. Paul had had mentioned that some of the links were broken. I went back and I looked at why, because the last pipeline that was built, it was only built for Libre SDR and not the other two, so that's why they were broken. So that, and then I still need to make the default application, the Hyperia one, which does the both receive and transmit together. Because right now the one that currently starts up with is just the downlink, with which creates the ton interface and you can ping through it, but it doesn't have any actual data being passed through there. So that's that. So because I made one for Hyperia, I made one for Opulent Voice. So I'll take comments and on it as well, just to put like an image to it. So Opulent Voice, a lot of progress in this regard. So again, restating the goals. First, what I'm working on is trying to get the standalone working with one channel and then move on to the bigger channel. And working on the Libre SDR. So just a progress update on my image. I was able to successfully build this past week. Ran into some issues stated here. Obviously, the one we talked about last time was having the right version of Vivado. That worked, and then I'm using Ubuntu 24.04, so there was some missing packages for the Vivado build, and then ran into some build root issues that I was able to get past. And then I installed the Vivado, and then I had to reinstall everything again because I needed Vitis for the embedded side. So once that started working, I was able to successfully get the SD card. And then at the same time, I'm using VirtualBox for virtualization on Windows 11, and it's a pain. You see this little green turtle, and that means it's not using the optimal settings for virtualization. So the VM was really slow. So just every time you get a Windows update, you have to do some crazy stuff in order to get it back to yeah. So I think I'm at the point where I'm just going to get rid of Windows. So that's update on that. So well, you guys are going to report that in a second. So I have a build process that works. I also worked on, so in the C++ mod repository, in order to match what Pluto MSK has at the preamble frame, I didn't see that inside the C++ implementation. So I added a -p argument that adds a preamble frame to help with acquisition of the burst. So I added that, and then I was able to run that through the simulation that I've got going. So some improvements to the simulation model that I have. Before I was only using the P and the PI loop filter. So now I added the integral arm, got that working. And then I added burst gating. So there's a burst detect, and then only when a burst is detected that it's going to update the timing error detection circuit. This allows for any subsequent bursts. It kind of keeps some of that, so it doesn't have to take too long to acquire. And then I took a deeper dive, so looking at the GTK wave, and I started noticing some discrepancies from my printouts that I wasn't getting the behavior that I was wanting from the frame sync. It was inconsistent. It turned out to be a misalignment in my frame sync VHDL module. After I got that, it was working as intended. So then I moved from simulation into hardware implementation. So this is a diagram of the places where I was able to move into hardware. So we got burst detect, and then what I call the MSK demod channel, which includes the polyphase match filter, which I'm not using because we're not using the half sign pulse right now. Gardner, TED time and error detector, the pi controller. Matthews is actually Matthews pi controller, and then a differential detector. The reason that's in orange is because I'm not where the state of it, the receiver is now, I'm not using that decision data from the differential detector right as of now. But I was able to, so this is a hardware, the burst detect implemented in hardware is showing no signal, and then when I turn the transmitter on, it'll go to burst detect. And right now I'm just replaying a file constantly, so it's going to stay, there's not really white space in between each of the frames. So just showing that it's just converting energy out, and then also Boolean going from true to false. There was some OpenCPI isms that tripped me up. I wasn't getting data to pass through, but I was able to fix that and get that working. So then moving on to the MSK demod channel. So I got this implemented in hardware, and I was finally, first picture of, what is each channel going to take as far as resource utilization, and then interpolate that out into our goal, which is 64 channels. So as it stands now, it fits in both this ZC706 and the ZC102. There's enough DSPs and registers in order to fit that. So we're still within the hardware limits to achieve individual demod chains for every channel, which technically, I don't know, it's debatable, but it just makes the design more complex if we were to share some over time share some of those. So then, since this is running hardware, I started looking at, is it working in hardware? So there's, with the OpenCPI, I'm allowed, I have the ability to write the outputs to file, and so I instrumented the timing circuit, so the symbols out from the time from the module, and being able to plot that out, and that's what you see on the bottom right. So a nice ring. So timing is working, but then when I differentially decoded this, and you would expect to have two blobs, one for 0 and one for 1, and I wasn't getting that. So then that led me to, this might be some carrier offset, because the way that I have this instrument on my bench is that I have two Libre SDRs. Well, one was, I started with a Pluto doing the transmit, then I moved over to a Libre SDR because it has a better clock. And then now, so at the moment I have two, one for transmit, one for receive. So then in order to compensate for the carrier offset, I decided to take a deep dive into what it would take to get the Libre SDRs clock reference. So there's two inputs into the FPGA. One is for pulse per second, and the other one is a 10 megahertz clock reference. So I went down that rabbit hole to get that implemented. So in the Libre SDR schematic, there's a DAC that feeds the voltage controlled, temperature controlled crystal oscillator that produces the 40 megahertz that's required for the analog devices transceiver chip. There's some buffering there, and then one copy goes to the FPGA and the other copy goes to the 809361. The DAC that's on the schematic is actually an 8-bit DAC, and I'll get to that in a second.
Right.
So yeah. So on the FPGA side, this is just showing where it's coming into the FPGA, the 10 megahertz, and then the DAC is controlled with a SPI interface, a one-way SPI interface. Those are the pins. So I think I decided to open up the Libre SDRs, and actually the hardware is the 7311. So it's a 12-bit, and it makes more sense because an 8-bit DAC only gives you step sizes of 0 to 255, which is not that big if you're trying to control one of these clocks.
Right.
So having the 12-bit, so it gives us more flexibility on kind of the jumps that the clock would make. So I confirmed that because I have 4 Libre SDRs total. 2 have the HamGeek symbols on it, and 2 have the Libre SDR symbol on it on the outside. And so I took the covers off and I validated both of those variants have the 12-bit DAC. And then I started testing my module that I'll go into the details in a little bit. And for some reason, when I got to the point where I was testing the transmit, the end-to-end, the Libre SDR labeled one was producing kind of not the spectrum that I was expecting. I guess, I don't know. And then at that point, I was like, the HamGeek's working. I'll investigate further later. So I have 2 HamGeeks SDRs on my bench, and that's what I'm using for the additional test that I'm going to describe in just a second. So this is kind of like an overview of what the voltage control, temperature control lock worker that I created. So I thought I had a 10 megahertz reference in my lab, but I don't. So I had to create one. So I got a Pi Pico, and I generated a 10 megahertz because luckily a 10 is not too bad. And the overall goal is to sync these 2 devices together. So it didn't have to be exact. So as long as they're from the same reference, that they would help with the carrier offset. So I got that built. And then so the worker itself takes 3 you can choose whether is the PPS source or it's the 10 megahertz source. I've only tested at the 10 megahertz or no sources at all, so just free running. And then it measures the 40 megahertz and then it calculates the error, again, using Matthew's PI controller, so you're getting a lot of reuse. And then it writes the DAC values out to the 7311, and then it updates the oscillator over and over again. So this is it, working with an OpenCPI. On the bottom right is a little picture of it. So I selected the 10 megahertz source, and it also detects whether it's present or not. So if it's not present, it defaults to none. And the midpoint is 2048, and then it will tune the clock such that it guarantees closer to 40 megahertz at the 89361 side. And then I hooked these up to both of the Libre SDRs, and then I had some issues with the circuitry. If it didn't like the GPIO's current. So anyway, I have 2 GPIOs, one for each of them. Yeah, fun times. So anyway, so now that I got that and I could roll away the carrier offset out of the way, this was my output from the clock recovery on the symbols out, and then differentially decoded. This is currently done in software. It's not doing it in HDL. But at this point, I was running up to an issue with, I guess, the timing, the circuit itself, the Gardner, because I'm trying to stick it into the current kind of band plan that we have, where we have 10 megahertz, 64 channels. but it's not an integer based sample. It's a fractional as regards to the samples per symbol. So I think that's where I'm getting some of these errors still occurring, because you should see a delineation between the top and the bottom half. So all that smear there is gonna be symbol errors. So what I did then was I shifted the modulator and the demodulator so that it is an integer multiple, and the circuit which was a lot more stable, because it's fractional. There's the time recovery needs a stable midpoint, and so it's either 2 clock cycles or 3 clock cycles, so it's always bouncing back and forward, so it never really locked. So I tried 2.5, I tried 288, and it always failed to converge in hardware. So I switched over to 3, and 3 works, because it's easier to find that midpoint, and is now able to stably locked. So what impacts does that have? I mean, so pushing to 3 samples per symbol decreases the receiver channel complexity, because I don't have to deal with that instability. But the existing channel plan would have to be modified slightly. I think this was discussed previously. I saw some Slack, and there's a document out there. So the current plan, like I mentioned, was 10 megs, 64, and that made each channel 156K. If we wanted to push our opulent voice to 3 samples per symbol, I would push that to 162 and some change. That would make the overall sample rate 10.4 megs. And then we can still do that and still be within the receive band plan, but we'll lose the edge channels from that. So propose that 60 channels are known good, and then the other ones would be out. But then it also affects the downlink as well, and it all depends on what the end state architecture of, if we're going to use the 89361 or not, but this is kind of feeds into the current implementation of Hi4i, that there's an interpolator rate of 4, so it has to run. So we're gonna bust that on the transmit side, essentially. So is it possible to bust that? Is it still okay? I'm sure. I mean, right now I think it'd be fine, but I'm just thinking ahead of some of those questions. So I think we can change the baud rate of the downlink such that we still meet within that 10 megs down, but we still need to investigate how to do that and test that in the lab. So there are some implications going. The alternative is to go to 2, but we're already really low in samples per symbol. Higher would be better, just so we can get cleaner clock synchronization.
Correct.
So this new sample rates works a little better in my favor, I guess, such that I know the C++ implementation used 40 samples per symbol. I went to 60, so that way that it's easier to decimate on the back end. So if I go up by 60, it puts me at 3.252 megahertz is the sample rate I set the 89361 to. And on the back down on the receive side, I decimate by 20, and it gets me exactly the 162,600, which would be the same sample rate that the channelizer output would give me. And that's the whole overall goal, is to get it working with the channelizer. So made those changes. So this is a success. So I'm able to transmit using this. These are still. Oh, this is free-running clock, so you can see there's clear delineation between 0 and 1 bits. There's still some that it doesn't have a great quality, but I am, and I'm not doing these the back to packets in hardware. I'm taking the decode IQ and then doing the differential decoding and then all the other framing stuff in software using a Python script. But I'm able to, out of 10 seconds of a transmit, I see about 250 frames worth of data, and then 240. Did it say that? Oh, this is the other one. It's only getting about 127, but After I use the 10 megahertz reference synchronization, so both are in the same, I guess, relatively clock because they're not exactly perfect. I get 100%. So all 247 are decoded, and it's a little bit sharper. Still don't know why I'm getting kind of that. I don't know, those blobs in different kind of semicircle-ish still, but I'm getting closer, if not getting all the packets. And this is still an RF loopback mode.
Okay,
So
so
there's still
RF loopback, like conducted RF loopback on a bench.
yes.
Okay.
Yes.
Yeah.
So one Libre SDR transmitting to another Libre SDR. Yeah. So next steps, going to knock out the rest of the hardware on the receive side, hopefully get frame sync done in hardware and validation of that. And then if time allows, the Viterbi decoding and interleaving all that other stuff as well that has been done before. And have an end-to-end receiver using OpenCPI. And then after that, is start looking at implementing the channelizer so that we could, my goal is to just at least get one channel through the channelizer to see if the receiver still functions as it's designed.
Right. That's a really, really good first test of a channelizer.
Yeah. Yep. So that's what I've done.
Wow, that's a lot. And you're dealing with directly with the samples per, essentially samples per symbol can be, well, that's the only traction that you get with reality really is,
Yeah.
your clock is ticking and how many samples per symbol are you getting? And very well taken about the non-integer relationship because that will cause some interesting things. So I think this is the right time to start paying really close attention to that to get it right for end to end over uplink and downlink, which is what you're firmly focused on. So yeah, let me see what I can do based on your results. The rotation around the constellation, we know where that comes from for the most part.
Mhm.
Grappling with synchronization, and that's the hardest part of digital communications. So something's a little odd there, and we'll figure it out. And this is amazing work and beautiful graphs, really lovely photos. And I cannot wait. Every week I look forward to hearing about this. And I just want to say thank you on behalf of all of us.
You're welcome. It's fun.
It sure is, but most of the time.
Yeah.
All right. Anything that you need or anything you don't have that you wish you could have or any confusing things that we should help you out with? Anything you're missing?
No, I think I'm good. I just need time. But everyone needs that.
True. That's the one thing we've had the hardest trouble procuring in terms of supplies is time. But yeah, the question about the sample rates of samples per symbol is, I think we need to probably go back and pay closer attention to that. We already know the VHDL implementation is what I would consider to be kind of grossly oversampled, but those are the clock rates that we have with the hardware that we have and the SDRs that we have. And um, that's, I would say, the person that would be like most interested in kind of like re-instrumenting it or going back and kind of refactoring it would be Matthew, and he is interested in that. So far, so good. It works. Moving to the C++ implementation or the C++ modem, the samples per symbol drops by kind of quite a bit, but it's still not critically sampled. But like you just mentioned, I don't think that we want to critically sample. We would like to be able to afford at least 10 samples per symbol, which is very traditional in sort of terrestrial UHF, VHF voice. 40 is kind of more than that, but it gives you some benefits. And if you can afford to spend the sample rate, then you should.
Yeah.
So, and I want to highlight something that you found out. So we've done this sort of calculation on paper to kind of prove that the ZCU102 and that this ZC706 and, this class of device can handle the design, the full design with the channel map and everything. And I think you're showing that, the utilization actually does kind of line up with that. And that is significant result and very appreciated. So it shows that what we have calculated on paper and sort of looked at and kind of expected is aligning with what we're actually seeing when you go through and you place and route and you make the circuit. So it's extremely good news and very inspirational and appreciated.
Great.
Yeah, good stuff. And true, I think you raised a point about like, how, because there's ways to share circuits and to like, I think if you've been around computing for a while, you know about bit slice. You go around and around, round robin, and you give everybody a slice of the processor and you context switch, all the way around. And this ran lots of offices and universities for a long time. And at least in the first deployment or first implementation, I would totally expect to just simply dedicate hardware for each channel in parallel and then not do anything super clever because, the cleverness has its own, debug.
It's always a trade-off. Yeah.
Yes, it's a trade-off. And there's these different techniques about sharing logic in an FPGA, and a super clever person could probably do it both at the same time, but this approach is better just to dedicate, like we're just going to duplicate the hardware for every channel. And this allows us to do some interesting things that if you're bit slicing or round robin, like in the successive interference cancellation sort of approach, then there are some higher level functions you can't really do. And if you just dedicate the hardware, then we can multiplex things and filter things and store things and provide some really innovative sort of communications to people. So that I think is the right sense. And it looks like we'll fit. We're going to add plenty more, but the numbers that you have here are in line with the ball. They're well in the ballpark of what we expected, and that is very good news. And it's really appreciated that you went through and actually did it to get the results. That's a tremendous value. Awesome. Any questions for Aaron or Paul? I think you've already made the SD cards for the devastations in the lab, but I don't think we have anything like to report back yet.
Yeah, that's true. I've got SD cards, 3 of them, 1 for each target. But I haven't plugged them into the targets yet, so
okay,
maybe soon.
Okay, yeah, and I'm happy to help. I'm familiar with like doing the Linux approach, like to booting them up with Linux and talking to them. I think it's going to be probably maybe similar to that, but I'll just follow.
It's very similar. It is very similar.
Okay.
Yep.
Then I'll just follow the instructions, and if there's any confusion, which trust me, I can find any confusing thing, I will trip over it.
Just let me know.
I will report back. And yeah, I'm really looking forward to this. And the stations are really cool. And yeah, just being able to take a design and then, oh, you want it here or here is it's magic. So I'm looking forward to it. We'll see what we can do. Yeah, thank you, Paul, for plowing through and getting it ready to test. Awesome. Yeah, and sorry, and I probably interrupted anybody that had questions for you. So I'll be quiet now.
Can we steal your external clock reference circuit and put it in our build? 'Cause that would be handy to have.
I think so. Yeah. I'll see. Right now it's built using OpenCPI, but we can take some of that stuff that was inside of it and get it connected.
And there are a lot of people out in the community probably would like to see that capability added to the Libre SDR standard build, because there's the connectors there and they don't do anything.
Yeah. I still have to test the GPS pulse per second. I haven't validated that yet.
Yeah, I don't know what you do with that on a standard SDR. I mean, synchronization at the 1 second level is usually not that exciting. It's frequency that you're more interested in.
Yeah, that's true.
Okay, next on the list is the opulent voice. We have a big VHDL update. And I'm going to give the floor to Paul so he can summarize and explain.
Oh, well, okay. You're more qualified to summarize what's changed in the VHDL. I've just been sitting around watching you work, helping with a little bit of a lab facility. So really, you should explain it.
Okay, well, I'll give a very brief summary. So as documented previously, we had, when we moved to over-the-air testing with 2 radios at different locations, we found out that there was a big missing transmit power thing. Like we were down 24 dB. 24 or 30 dB, really. And so we were very confused by this, went back to the HDL. We found the problem. Matthew fixed the problem. And we plowed right back into field testing and nothing worked. So when you change the transmitter power and you have had your receiver dealing with low power and you have been assuming that that is the correct dynamic range, the correct number of bits, the correct levels in the simulation, you tend to design your control loops and your thresholds around getting not enough power. So we wrote this up for the newsletter, went out for the March newsletter, just tell how was the transmitter fixed. And then we'll just clean up the receiver. It turns out that there was more wrong with the receiver than we thought at first. And we picked through and we were systematic about it. And we found that there had to be missing receiver power after the transmitter was healthy, and we proved that the AGC was working through a series of experiments. The AGC levels were being delivered all the way up to the integrate and dump in the demodulator. For the MSK demodulator, it does a whole bunch of really neat math because minimum shift keying is really cool. And it has a section in there called integrate and dump. So integrating up the power, and then here you go. Here's the result. Okay, so IND, integrate and dump. And the numbers out of that looked really low. Oh, this must be because now the proportional and integral gain coefficients are now wrong, because now you're getting a much louder signal. So, oh, well, maybe we just tuned the PI gains to the wrong positions, wrong values. So we did a couple of tests, but they actually looked pretty good. Went back into the code again, because you know what? When you get confusing results and doesn't really see, you need to back up all the way, clear your mind, and reapproach. And sure enough, we found that yes, the problem was in integrate and dump. No, the problem was not the PI gains. They're actually pretty good. They look like they actually may be the right gains, even with the big change in the transmitter power. It turns out that there was a right shift of 5 bits in the soft information output. So we have hard and soft information generated in parallel in our design. A hard bit decision is you just make a call 0 or 1, and that's it. You just deliver best guess. Soft information is how sure were you that it was a 0 or a 1 that you got? If you have a high signal to noise ratio, you're going to be pretty sure. It's going to be bang, bang, one or the other. If you have a low signal to noise ratio, the lower your SNR goes, the more noise you have, the harder it is to kind of hear the voice on the other side, those 0s and 1s. You're kind of sure, but not very. And information like that is really important because you can use it to make your signal decisions better. And this is when we talk about soft decisions. This is exactly what we're talking about. MSK DMOD gives you both. The hard decision is the sign bit, 0, 1, and the rest of the big long number that you calculate is essentially the probability of it being a 1 or a 0. So it's just one floating point number, but two sort of audiences. And so what we were doing in the integrate and dump is at some point back in October 2024, Matthew said, wow, I'm overflowing one of the registers here in the demodulator. I don't know why, but if I shift it right 5 bits, it works. This needs to be reviewed. It's clear in the comment. Making this to where we don't overflow needs to be reviewed. So we're reviewing it now. we have now, I was like, that's weird. This is a shift by 5 is how many bits? 32x, right? It's about how much missing power we had in the receiver. So I'm like, oh, well, one number, 5 to 1. So I recalculated all of the registers. You can't go to 0, a shift of 0, or it will overflow. So Matthew's totally right. If you don't handle this after a multiplication, you can overflow your registers and it all goes to hell. So 1 bit of 1, assuming you have full, complete use of all, like everything is maxed out all the way through the receiver, you never want to overflow. You need a shift right of 1. Just go over, make it a little calmer. Shift to 5, way too much. Okay, change that, kapow. It all came alive. We had, and in order to make this work, the thresholds for the frame sync detector had to increase because now you have a larger value. Okay, great. And then we had to go back in and say, okay, to quantize your information, quantize the soft data, you don't want to deal with 32 or 16 bits. Let's deal with like 7 levels. So 0 through 7. That's the quantizer that goes into the forward error correction. You turn that probability into, so if you've ever been asked like in a survey, like, hey, could you tell me on a scale of 1 to 5 if you like this restaurant? Your brain can go, yeah, I can give you 1 to 5. If you don't want to give like 1 to 32,000 as a scale, it doesn't really make any sense. Do you really like the restaurant? Do you not like the restaurant? Right in the middle or So we quantized the soft information. That scale had to be redone because now all of a sudden, well, everything would be squished all the way to the end of the scale. Okay, fix that. And then there was something else that had to be fixed. It was like at 11 o'clock at night. And then it all worked. And I think I'll hand it back over to you to talk about what happened in the lab today because, the completely broken radio, I think, actually worked.
Yeah, a lot of stuff has come back to life. Working at pretty much as it did before, we started trying to get back the 24 to 30 dB of gain on the transmit side, which caused some side effects that were not entirely anticipated. So last night we got basically working. We were able to do a loop back, and I was also able to have one SDR transmit and the other receive, and that worked not perfectly. There's still a bunch of things that need to be tuned. We're in a whole new working range now, so everything needs to be retuned. And then the PI gains have always needed to be tuned, so they probably still need to be tuned. But we got a working set that seems quite solid for lab work, so it's no longer in our way. So last night before we gave up for the third time and decided it was time to quit for the night, we set some goals for this morning, and we've achieved all of them. I think all 3 of them. The first thing I wanted to do was finally make a working version of the B-sides demo, which is 2 Libre SDRs on 2 different frequency bands, one transmitting on each frequency band and listening on the opposite frequency band, but inverted so that they can hear each other. So a full duplex, like you'd have if you were working through a satellite, or even a terrestrial repeater if it was a crossband repeater. This enables us to transmit and receive simultaneously and see if that works. And it's just a matter of plumbing and making a new version of Dialogus to set the frequencies to appropriately inverse values. And that I did that this morning, and it worked. I'm able to receive messages while transmitting voice. I'm able to, actually, I didn't try transmitting voice at the same time because it's difficult to tell whether it worked or not with two microphones and two speakers right next to each other. Need a couple of people with some separation and headphones and stuff like that to really test that. But it seems like it's working. Before we had that almost working before B-sides, it seemed like there was maybe some kind of a CPU load problem where everything got kind of glitchy when you had both transmit and receive happening simultaneously. And I'm not seeing that yet today. So maybe that was some other problem that is now gone. That's the first thing I wanted to do, the full duplex demo. And that successfully works. It's just barely working. We got it to work once briefly, a couple of times. It's not rock solid yet. There's more work to do, but that's been done. The second thing we wanted to do, I'm looking over at my whiteboard, was to try to do the house-to-house demo. This is where we originally were forced to focus on the missing 24 to 30 dB. We have next door houses, and it should be possible to close that link with a milliwatt, the 0 dBm level signal that the SDRs put out. And sure enough, it is. We got that working too. Michelle has at her house a Libre SDR, and once we told it to transmit its maximum power, I was able to receive it just fine over here. We only went one direction because we ran out of time. We're working at 70 centimeters, 430, 1.35 megahertz is the channel we chose because it sort of fits into the band plan because we have antennas for that band. And the third thing I wanted to do was to characterize that power amplifier that Oscar recommended we try, that he had success with the UPR sounding rocket launches. And I did that too. I have not yet transmitted the waveform through it. That'll be the next thing. But I went into the lab where all the test equipment is, in the remote lab, power supplies and signal generators and stuff. And I hooked up a ham radio power meter. It's a Yaesu meter that covers up through 70 centimeters and can do up to 200 watts, and a dummy load that can do 15 watts. And then measured the output power from the power amp for various input powers. And, here's my results written down in this notebook. The answer is I can get a full 8 watts out of that amplifier with 0 dBm input. Whoa. That's miraculous. I forgot I had sent you a picture of that. So here's the output. It uses about almost 3 amps of current at 12 volts, which is pretty inefficient, but I guess it must be a Class A amplifier. And you really do need 0 dBm to get the full 8 watts out. But you can dial it back to anything you want, down to about 1.5 watts or so. And below that, it just turns off. It won't give you less than about 1.5 watts. It uses about 1/3 of an amp, which is several watts, just sitting there with no signal going through it. I was kind of hoping for a lower standby current, but this is what we got. I tested one of the 3 amplifiers that we've made, or that we bought rather. So this is preliminary information, and that Yaesu meter is not fine test equipment. Just gives you a ballpark number, and there's lots of cable losses and adapters and things because it's kludged together. The Yaesu meter has UHF connectors on it, so-called. So adapters are necessary to hook it up to anything real. But this is what we've done. We've managed these 3 things. We can see things that need to be tuned. In the Dialogos output, you can see that the symbol lock detector is way too forgiving and sensitive. It'll call lock on noise.
Right.
Flickering in and out.
The thresholds for the symbol lock are still tuned for a really quiet signal. So they're just going to say, oh, anything that shows up, they're going to lock. And there's another factor in there is the window of time that you integrate, and the amount of time that you spend gathering it up is also configurable. So we have time and also threshold to tune in the a symbol lock. Matthew brought this up, and this is, this is a very solid mainstream. This is a design that people use, and he's made it pretty clear that these thresholds and the window is important, and that getting good information will allow us to make good decisions. These are status reporting. The whether or not the symbol has locked is a status reporting, but the amount of integration time and the threshold are key. So it's not a single dimension, but it's two dimensions of the results. So Matthew, as soon as he's back, is going to be paying close attention to that. And we're also going to do all that we can to make sure that the symbol lock is accurate and well done.
Yeah. There's one thing that didn't quite, I don't think got mentioned in your explanation is AGC. This receiver has AGC turned on. So for a wide range of power levels at the antenna connector, it gets about the same power level on the digital side after it's been sampled, because it's all that AGC happens in analog circuitry before it gets sampled. So we had a strong expectation that there'd be no coupling between transmit and receive, that a transmit level that was 30 dB down would be almost the same as a full power transmit, because AGC would bring it up or not knock it down as much. And so when we had receive problems after correcting a transmit gain problem, we were a little puzzled. I'm not sure we completely understand exactly how that happened. But there are lots of interesting interactions. And to make it work in simulation, where all your work is in the digital domain, you have to simulate the levels. So the transmit levels have to get wrapped around into the receiver digitally without any help from AGC. So getting it working again in simulation obviously did require some help, and you added, Michelle, a gain adjuster in there to compensate, to bring it up to the level that we were actually expecting to receive. So there's interesting stuff going on, much of which we understand.
And almost all of which we can test. So yeah, we're in good shape. All right. Anything else about the HDL? All right. All of this work is up to date in the repository. So it's the repository is on GitHub. It's at Open Research Institute. It's called Pluto _MSK, even though that's just one of the implementations. And the branch that we're talking about, where all of this work is the TX_sample_sync. So TX sample sync branch. And very soon, I think, based on the results that we're talking about here today, we're going to bring that branch back into main, so that all of these things, all the fixes will actually be back in the main branch. Because right now, the main branch is low on power, transmit power, has the old frame sync methodology. The frame sync detector is actually improved throughout this debugging process. It's been rewritten. The receiver fixes are in there. It's much better. So I think now is the time to go ahead and bring it all back into the main repository, so that we don't have these branches off to the side for development. And yeah, good stuff. That will also give us a chance to really kind of dig in on the things that Aaron has brought up, and about really looking at like the sample rate, samples per second, samples per symbol, sorry, and all of that aspect of the control loops, because it has a directly affects the quality of the signal. So yeah, really good stuff. Rapid progress after a pretty big setback, finding that we were missing a whopping 24 dB of transmit power. So that's where we're at.
Yeah. The Dialogus is similarly off on a branch, and we'll be merging in soon.
Cool.
An
No
interesting,
error blockage or changes, I don't think.
no, it hasn't actually changed much in a couple of months. It's been a stalwart.
Good deal. All right. Anything else, Paul?
One thing that I noticed that is not quite actionable yet, but may turn into something useful. On Crowd Supply, I noticed somebody has announced a project, um, to create little boards that are kind of like Libre SDRs, but using UltraScale Plus devices. Uh, Price is not announced yet, but they look like they could be made pretty cheap, like a Libre SDR, depending on how cheap they can get the UltraScale Plus devices. So these might be a good development platform. We should at least keep our eye on it and see what becomes of it, and check and see if the device they're using is actually big enough for us to prototype on.
Outstanding.
The
Okay.
search term to look for is PZSDR. I think PZ refers to the name of the organization or company that's doing it. And they have two different models, and don't quite understand why, but they're both Zinc UltraScale Plus devices. One of them uses an RF SoC, and the other one uses the radio chip.
Oh,
I think
wow.
that's the reason why
Okay.
they're different.
I'm going to take a guess at why the price hasn't been announced if they're using the RF SoC, which when it came out was a 5-figure chip.
Yeah, well, that doesn't. I'd be surprised if something in 5 figures showed up on Crowd Supply, frankly. And it's standard for them to not release the price until after the
Right.
project is really begun. They
Yeah,
have to
that's
start when they're ready to
totally.
start taking donations or contributions or shares or whatever it is they're selling. Then there'll be a price.
Okay. Yeah, thank
But
you.
this is
That's
interesting.
absolutely worth tracking.
Yeah,
Okay.
and OpenCPI has support for those things, and we could probably get, or actually both, even the RFS OC, we can get the same stuff we've been working on, or at least I've been working on those platforms as well once they come out.
Outstanding.
Yeah, that's what it's all about.
Absolutely. Okay. Yeah, well, I'll help keep an eye out, and thanks for spotting that, because that's essentially the board we'd have to build is something along those lines. So any traction we can get there makes everything happen much quicker.
Let's see if they say anything about open source. I'm not seeing it right away. Yeah, there it is. Permissible open source license. And they plan to also release bare metal test code, compatible firmware, open Wi-Fi test firmware, and more.
Outstanding. Okay, I think that sounds useful, and we'll keep an eye on it.
Yeah.
Very good.
Well, more things to buy for the remote lab.
That's right. Thank you so much. Okay, so I have an update about Earth, Venus, Earth. We have multiple sites that are participating coming up in October of 2026 for the inferior conjunction of Venus. We're going to attempt to bounce communication signals off of Venus and not just a radar return. The communications protocol design for Eve is coming together. Pete Wyckoff has led that. And in simulations, Monte Carlo and just information theory kind of simulations, this is looking really good. This is a channel that is not normally tackled by communications designers because of the coherence time limitations due to Doppler spread of Venus. It's a very challenging channel because of Doppler spread. And the results so far are very interesting because they line up with a lot of information theory, as you would hope and expect. But again, since there's not a lot of literature here and people tend to stay away from these channels, not really tackled very often. So this is very exciting just from an information theory point of view and a protocol design point of view. So things look good. The SIGMF files are ready to go. And what we're doing is trying to build some EME or Earth, Moon, Earth stations to try them out. And lots of progress there over the past week. The first parts have come in for an EME station. This is going to be a relatively small or modest EME station on purpose. The protocol is designed for a 0 dB in 1 hertz channel. And turns out that if you have a 39, 40-inch offset feed dish at 2.3 gig, and you have a 20-watt PA with reasonable performance and a decent transverter and a pretty good LNA, you can actually duplicate the EVE link with some margin through the Moon channel. So exciting stuff. We have 2 volunteers now. Loretta from Artemis 2 with their 10-foot dish is very interested and tuning up her dish for that. And another volunteer, Mike in Massachusetts, is putting together a station as well. And then when we're kind of reasonably sure that we've got our stuff worked out, then we'll open this up and ask other people that do EME at 2304 megahertz or 2.3 gigahertz to participate to try out the protocol. And yeah, very exciting. So that's moving forward pretty quickly. That will give us real world over the air to a yeah, bouncing off of a surface of a, not a planet, but a moon, but, lots of confidence about moving forward with EVE that yes, this signal should work for Venus. The link budget has been updated multiple times over the past week. The link analysis, the major step forward for that is the inclusion of all of the content for both of the proposals to Effelsburg and to GBO, Green Bank Observatory. These two sites are receive only, and since the concern is here, like what if you don't receive the signal that you sent? Since it's a very tough channel, and let's say that Dwingelo or DSES or Bockham or any of the other sites that might participate are transmitting and then don't receive their signal. What I'd like to do is provide solid receive coverage for any time that Venus is up, and that these two really large sites are also visible. And that would be GBO or Green Bank Telescope, Green Bank Observatory. This is a 100-meter dish, which gives you at least 12 dB extra gain. And I have applied we have a proposal, a draft proposal at GBO. This is a complicated process. I've spent about 40 hours on it already with the help of 5 or 6 people, including the help desk and the IT people at GBO, to sort out all of the different things that you have to do in order to get a proposal through the process at GBO. We'll be asking for 4 sessions, 2 sessions at 1299.5 megahertz for Dwingelo or anybody else that's at that frequency, 2 sessions at 2.3 gig or 2304 megahertz. There is a very interesting problem at GBO because they have a permanently installed notch filter at allegedly 2300 to I think 2330 or 2360, which by the way is right, we're right at the edge. When we go to the breakthrough listen results, we see that it actually kicks in at 2310. So I've asked for clarification on exactly how their notch filter is characterized so that we don't have to ask stations that want to participate to move to above the notch filter, which would also be above all of the Sirius XM satellite band. That's why they have the notch filter, to filter out these powerful stations from their very sensitive instrument. Okay, so that's proceeding. We have not pulled the trigger. The proposal is still draft. There's people that are looking at it at GBO, but we have not officially applied for time at GBO. But we have applied. We completed the application process, or at least the transmission of the proposal to Effelsburg. That is another 100-meter dish steerable in Germany in a relatively quiet site. They were very interested in participating. The Effelsburg site is very close to Dwingelo, and that's where we'll probably center, it'll be an EU site. DSES actually does have several windows with Effelsburg, and can try to get, as a backup, they can try with Effelsburg. But GBO is the one to use for a site like DSES. So cross your fingers that both of these very large scientific instruments in radio astronomy will say yes to the proposal. Cross your fingers that all of the sites, DSES, Bockham, Dwingelo, and there's others out there that would like to transmit. And with a 100-meter dish, this brings the diameter of the dish down to where smaller dishes like 10 meters, at a lot of universities can also participate. So we can have a true citizen science sort of experience. The more people participating is good. Our job at ORI is to coordinate different people at different times transmitting. We We do have at least one window of time where both 100-meter dishes are capturing at the same time. That is really cool. So if anybody is up and ready to transmit, having two different dishes on two very different parts of the planet to capture your reflected signal, that's kind of a best case scenario. Okay, so that's where we're at as of today. I've talked with Thomas at Doingalo, so he knows about this. They still have to ask for regulatory permission. They're still in the process of doing that and figuring out the dates. I have a set of times. We've asked for a 2.5 hour window of operation on the 4 dates. The 4 dates are, the 2 middle dates are the inferior conjunction itself and then the best day. These are 3 days apart. And I learned something that maybe a lot of you already know, but I didn't. When I hear inferior conjunction of Venus, I think that that's the point where Earth and Venus are closest. And it turns out that's not exactly the case. The inferior conjunction is defined where the ecliptic lines up, where the alignment of Earth and Venus and the sun occurs. It turns out that 3 days later, that's on October 22nd, but it turns out 3 days later, they're actually the closest, physically closest. So we have asked for sessions on both of those days, on the actual inferior conjunction itself and where Earth and Venus are physically closest. It's less than a dB difference, but it's a difference. It's clearly there in the data. And that was what kind of drew my attention to this and caused me to kind of appreciate the difference in the definition. Because I've been saying for over a year, inferior conjunction is when Earth and Venus are closest. That's not technically true. They're aligned, and the closest is on the 25th of October, not the 22nd. Also, on the 25th, you have a slightly better albedo. The dynamic albedo gives you a little bit of a boost too. So we've asked for sessions on both of those dates, 3 days apart. The conjunction itself, the closest, where you're actually closest, and then a little further out on those weekends, further out. You really don't lose that much in terms of path loss. You're still actually pretty good. So this is 4 sessions. 2 are on L band, 2 on S band. We're trying very hard to make it possible for people to participate, to try at least once. If they have a problem, they can try again. And then we're using both frequencies. There's a set of times. These dates are the same, but the times, the windows may be a little different for Effelsburg versus GBO. And so we'll be able to publish a one-stop shop kind of graph that shows like these are the, assuming that they accept the proposals. We'll say, hey, this is what it looks like. Tune in. Let us know when you're going to transmit so you don't stomp on somebody else. And then we get the IQ recordings back from GBO and back from Effelsburg. And we've asked for them to record, with enough resolution, and also to have, here's the Doppler corrections, and we'll be able to do the exact same thing that Doingalo and Stockert did in March of 2025, and that's to present the data set. Here's a decimated data set. Here's the corrections in the Doppler. You can take it, and oh, by the way, here's an example Jupyter notebook on getting the signal out. And then if you know that there's, for 2.5 hours, if you transmitted 13 minutes to 27 minutes or the entire time or whatever, your 4-minute blocks, then you can go in and you can see if your data is in there. And other people then can go in and see if your data is in there. And you should, if all goes well, get some really good news for the first time, an information signal out of a very, very difficult channel. Okay, so that's my update about the process of getting some big guns, receive only big guns, but some big gun stations to listen at 4 sessions, 2.5 hours each, spread out over, plus and minus as Venus approaches at the conjunction itself at the best possible time where we're literally the closest, and then a weekend on either side. So that's what I've been up to. All of this is up to date in the EVE repository on GitHub, and please take a look at it. in case I've botched some sort of date, all of this stuff really could use a review. I trust Skyfield and all of the work that we've done and the dozen or so people that have already looked at it. But you only find problems with your conclusions and data by continuing to keep looking at it. So please take a look at the notebook. And the new additions are a planner, so you can put in which of the data classes. We have a data class per site, and you can turn all of them on, one on, two or three of them on, and you can see which ones, it shows you the visibility of Venus. So it's basically who else can I talk to? It's a sort of a communications planner graphic in the link budget now. So that's the new addition over the past week. I think that covers item 3 and 4 on our list. So I'm going to stop here and answer questions about any of this. Questions, if anybody has any guidance for me or advice or pointers or any other sites that they know about. The final item on my list is Arcanum. That's it's an open source conformal method of moments antenna analysis software. We have 4 phases, and phase 1 has been complete. And we have put out the call for people to come in and do analysis and to contribute. This is in Rust. To contribute for phase 2. Phase 1 was the geometry of the wire antenna, and that has passed all the unit tests. We actually had a really good cycle of revising the testing and validation. There were some cases that we missed, and at least one place where it was awkward, not entirely correct. We're now very confident the validation is good, and the code submitted passes validation. The second phase has to do with the sort of electrical analysis of the wire antenna itself to kind of take your geometry, convert it into an electrical set of signals. And phase 3 would be the electromagnetics. So now you have an electrical representation. Phase 3 is all about the actual antenna analysis. And then phase 4 is how you present the results, how you visualize the results to make them useful to a human or to some other program. So phase 1 done. Very good work, mainly by Steve Conklin. And we're giving him feedback on essentially like how to set up the, if you've done Rust before, it's crates and, the whole Rust mindset. To be able to duplicate the results and to participate in the development, the README and the instructions do need to be refined a bit. I think Paul helped on that. So please dive in for Arcanum and give it a shot and let us know where it breaks for you in getting it set up, because that's kind of where we are in terms of updating the documentation. The validation looks really good. So we now have a wire geometry for antennas. And like I said, the next step is electrical. After that is electromagnetic. After that is visualization. You go from one phase to the next. You don't go back. So it's a flow graph through for antenna analysis. What we do not have is a way for you to edit up the NEC file. We talked about that last week. There's options out there. The phase 0 could be added. That would make this a really nice useful package if you could also design an antenna instead of just ingest a .nec file. Okay, that's all I've got for the list. So I will now turn the floor over for office hours. Any open discussion or any questions about anything that we've talked about?
Any updates on MDT?
Oh, yes. I've been running the MDT experiment after I got the SPI communication sorted out. What I did is I turned it on, left it on to see if there was any weird memory problems or anything like that. It's literally been running for many, many days. What I've been focusing on is for the MDT, for the AMSAT UK 30 kilohertz channelizer. And I have not yet, because this hardware won't handle it, the ICE40 won't hold it. So I have not yet moved it over to a larger FPGA to test the Hyper-IA design that's based on it. So I don't have any good or bad news about that. But everything is up to date in the repository for MDT for SIC, and it was just a really good experience. It's always good when you see something working. It's generating its own kind of test vectors right now. So what it's doing is essentially fake data because there's no radio attached to either the STM or the ICE40. So it's looking at signals that are fake. So it's looking at like IQ information with like 4 signals of varying strength. And the next step on that would be like go ahead and prove that maybe the next step would be randomly generate every time you turn it on that you get a random for 3 or 4 or 5 signals of maybe various types. That's some work, but rather than like try to get a radio working and then listen to a band like the FM broadcast band or something like that, just go ahead, generate the IQs, and every time it pops up that you have a random selection, and this would be a test. Go ahead and then see how many can you handle. 4? Can you handle 5? Can you handle 6? Where does it break down in terms of the round robin sort of like, okay, when do I really run out of time? Because that's what I really want to know. So that would be the kind of the next step, but it's stable and producing the results at speed. So I think the last time that I did a serious presentation, it was actually kind of slowed down so that you could see the LED, the status LEDs, flashing, and it would very slowly present to you IQ information. I now just ran it up to the real sample rate, and it handled it, and it spews out the results far faster than my eye can see. So that's been the good news. I mean, there's still some headroom. So looking at like that was one thing I was worried about was can it talk fast enough between the FPGA and the STM? Having gotten kind of used to a zinc where you have an ARM and the FPGA fabric right like those problems about throughput getting on and off the general purpose processor to the FPGA. It's nice to not have to worry about that, but it can kind of spoil you a little bit. So that was one of the things I was like, oh, it looks like it would work on paper, but I was very concerned about that. But we actually have quite a bit of headroom left. Now the current specification, the STM that's specified is kind of a high-end STM. The FPGA is the ICE40, which is a very good choice, for it's frugal, kind of low power, it's not running at 2 watts, it's less than half a watt. 2 watts for like the zinc 7010, for instance, can draw like that much power through the Pluto, right? But that STM is pulling an awful lot of current, and it's kind of overspecified for the mission. So that doesn't really affect us on high Faria at all, but like I'm concerned about this particular part. The STM is totally fine doing all this processing and handling the successive interference cancellation for MDT, but we bust the current budget. I'm not sure that was actually looked at very closely in the beginning when it was specified. So I'm a little concerned. I think we're going to have to essentially derate the STM once we are really sure how much processing needs to be done by the STM, because we're already at almost 87% utilization on the FPGA, and we had to offload actually one of the mathematical functions from the FPGA already. So the FPGA for for the ICE40, 30 kilohertz for AMSAT UK, handling what it does pretty well, very stable, happy with the design. And now we have to say, okay, we have an overspecified STM and now bring it back down and hopefully lower the power to come in under their budget. So that's where it is as of today.
Is ORI still going to spin a board for this, or is it just proving out that the design is going to work?
I haven't heard back from AMSAT UK yet.
Okay.
It's been 3 weeks since I have, and the last I heard, they were going to write an article and make some decisions about it. Because yes, I think given the time constraints, even with the schedule being relaxed, and the launch essentially put off from 1 whole year. Like, even with that sort of schedule pressure reduction, I don't. Okay, so just pure speculation on my part. So I apologize to anybody listening to this, that I don't want you to cringe and say I'm talking out of turn or speaking for AMSAT UK. I'm not. But my instinct here is that we actually do need to go from what we're doing here with the 2 separate dev boards with jumper wires to prove out the design and to show that it actually does work at these speeds, that we just need to go ahead straight to the flight hardware board layout design, like an intermediate board from a volunteer team, from amateur team, even from a university team. We shouldn't do that. We should just start working on the board. And I don't get the sense that there's anybody else that would do it. I think that it would be up to us to sort of go ahead and do the hardware layout.
Where do you find like the specifications that it needs to meet as far as form factor and connectors to the, I guess, since this is a payload?
Yeah, that would be from AMSAT UK. And to my understanding is that they have outlined that. And it's in like their slide decks from talking about the FunCube Plus. Not my strongest area, but like the 1U form factor and the selection of the the interfaces and the connectors has been defined.
Okay.
So they would be the ones to say so. I can find out, or we can move forward and see.
Yeah, if there's a link or something, that'd be helpful just to see what it would entail.
Yeah, it may not be a link as much as here's the current slide deck from
from
AMSAT. So that may be what it is. I am not a board layout person. That's not a skill that I have a lot of skill in or anything like that. So I want to be very cautious in saying, anything about what I've seen in the presentations. It looks very compelling and clear, and the folks that were working on it before were happy with the specifications from AMSAT UK. We really do need somebody to kind of take that on and to give us a solid, like, okay, I see what you're doing here. Here's the layout, and to move forward with it. And I have one person that said they were interested, and they're now on our Slack. So I just don't know yet from AMSAT UK if we get a solid thumbs up to go ahead and do that, or if they have somebody lined up.
Okay. Yeah.
That sounds
Plenty
like
of do.
that sounds like
It's something that
I should go track down.
Yeah.
I've
done a couple, nothing that's actually flown, but yeah, I've designed some but there's plenty of stuff to do, so I don't want to add more to my plate.
Yeah. No, I'll be sure to I'll ask around and I'll put it on our Slack, and we'll see what we can kind of find out. And because we just really want this to happen. It's a really, really neat design. It really showcases like the power of multi-rate processing and digital design in general. And it's a really neat thing. And they have space on the spacecraft, and it's we should do all that we can. The very happy with the way that the design looks in simulation and in operation, without and we now know like what the IF looks like and what we're going to get. So we have a lot of the pieces. I think that the best thing that I could do is like go back and press a little harder for some decisions, some status, and to make it clear how we can meet them to provide working hardware.
Yeah. Super excited that the Pluto MSK is in a better state. So I do plan on pulling the branch that you mentioned and getting that built and tested and seeing how it does against Charlie. So yeah.
Yeah, I think one of the things we'll do is to go back to an interoperability sort of test, which was one of the nicest things over like the past month or so was, the C++ modem, received and, receiving and transmitting back and forth to the Libre SDR modem. There's nothing quite like that working to really make your day. So we should, not want to jinx it, but we should be able to get back to that as of today, really. So that may be something that we go ahead and try. And yeah, for interoperability, like you implement it and you implement it, better work.
Yeah.
And that's where you discover a whole lot of problems. And that's going to give you the most traction on identifying and improving the design. And then now with the third implementation is phenomenal. That's really that's fantastic. I think if we can get then like here we go, everybody can hear everybody, everybody can be heard by everybody, and that that's going to ring out the protocol pretty darn well. Yeah, Rick, I have a question for you about DSES and the and Eve. I don't yet have an answer back about the notch filter at Green Bank. They have a notch filter, a superconducting notch filter, which is pretty neat. From 2300 to like 2330 or 2360 megahertz, but the breakthrough listen data shows that it really kicks in at 2310. So I've asked for clarification from the Science Help Desk, which revealed that my account cannot access the Science Help Desk at Green Bank. And so I've been working with the IT staff to get. So meanwhile, I just put it into the proposal and tried to write the folks directly. So the question to you is, in case it's a total disaster and they say 2304 doesn't work at all, is there any way to move above that? Are there any agility at all for the 2304 and maybe go up to like 2390, which actually has some advantages because it's a little bit better, just a little, in terms of local interference. Not that you have to worry about that very much at DSES, but I'm just curious, is that if we had to move in order to get caught by a 100-meter dish, would that be enough to like, is it physically possible for DSES to move to that frequency? And then is it like politically possible to move from 2304?
It's certainly possible because we have not built any hardware yet. So I guess we can build what we need.
Right on. Understood.
The hardware will be based on SDR D210 type technology. So frequency there is not a problem. The only problem would be if we had a filters or if the Q of the feed was high, which is highly unlikely. So yeah, I don't see any problem.
Okay, thank you. I think it's going to be okay, really.
As long as it's legal.
Yeah.
And the band at full 1500 watts, we're good.
Yeah, it is. It's just, the reason that they have the notch filter is to filter out, Sirius XM satellites. But the actual like printing, like the spec for their notch filter is all the way down at 2300. That's kind of low, there's.
Now that you mentioned it, whether we should have such a filter also.
Oh, well, that's a really good question. I don't know. I think
those very strong signals
yeah.
on a wideband receiver can limit our dynamic range significantly. And that can be a problem I hadn't thought of. So
yeah. Okay, good point.
just we haven't put anything together yet. That's
okay.
I wonder if anybody makes a filter that would be helpful.
Well, apparently they have a superconducting notch filter.
I said somebody makes something helpful.
I know. I was like really impressed.
That's
I
not it.
know. I was like a superconducting notch filter to punch out satellites for a 100-meter dish. I'm like, wow, somebody has a more interesting job than most of us. That is pretty
I
cool.
told the guys at Haystack Observatory, they do similar kind of things. And I said, well, I don't think we can do, from a practical point of view, liquid helium, but perhaps, nitrogen. You can go buy liquid nitrogen, and that's not really, really cold, but it's colder than the atmosphere. How about that? And they said, that's no good. It's too warm. Well, okay.
Wow.
So,
Never a dull moment. That's amazing. Yeah. No, we're so fortunate to be able to work on things like this, and the experience of like reaching out to GBO and Effelsburg and talking with both, people at both sites has been super positive. I was, ready for it to be, a proposal experience that may be maybe a little more formal or negative, or beat it, we just want to talk to universities or PhDs. No, it's been a very, very positive experience. I really hope that they accept the proposals and that we get to work with them, and that this will maybe provide like a motivation to pull things together at sites like DSES or Bockham or Dwingelo, to really kind of like, yeah, okay, so you have a really big site listening. It takes some pressure off, and gives you a pretty substantial margin to do something really cool. So I'm hoping that this helps. And wow, I have learned a ton. These sites are amazing.
but you can't access the help desk because that's highly secure.
Yeah. The help desk is highly secure because I cannot log in.
Very wrong there.
Yeah. Well, yeah, because you're supposed to be able to. And then the IT people. So there's the help desk for the science part. There's a whole help. That's what I'm trying to get to, is the help desk that's there to help you with your proposal, to answer scientific questions or technical questions about your technical or your scientific justification for your proposal. And then the IT people, which is who I've been talking to, are their help access, account problems, log in to get your institution properly, in there and all of that. And they've been great. And they're baffled as to why I can't log in. So this is an unusual problem. So I've yet once again found an edge case. I'm good
There's an organization which is an offshoot actually of DSES, started by some people from DSES a long time ago, that has access to Greenbank. And any of its members, I'm a life member, any of its members can sign up for access to Greenbank time without any proposals or anything. Just sign up. And that's the Sarah group. And so you might want to ask them, if you run into a roadblock, how to bypass the roadblock. But the Sarah president lives just 10 miles down the road from me here.
Okay. Well, you know what? Because our draft proposal is almost, if I hit submit today, I wouldn't feel bad.
Yeah.
I'm waiting for, I've got the question about the notch filter in there, in the proposal itself. So if I don't hear back today or tomorrow, maybe I'll just go ahead and submit it. If they say no, then I'll take the exact same content from the proposal and go to Sarah and say, is there any way you guys can just record for us on these 4 dates? Can you just handle it? And if that's a way to get it done, then that's a way to get it done. So I'll take your advice and I'll, keep it in mind. I'm very familiar with Sarah. So
good.
Yeah, I think that's a good backup to the to the process here. It's and we're already kind of like so our proposal is in the category of the director's discretionary time and not one of the more formal scientific, slots. And the times that we're asking for are actually low demand times at the observatory. So odds are pretty good that it'll go through. If there's anything that happens to it and they say no, or then I'll definitely take advantage of the Sarah angle. That's a super useful advice.